BHA, what happens with a steerable system? Yeah, you can steer it, you can lock through it. But what happens when you have to pull that BHA out of the hole? You have the risk of sticking pipe. So not only are you having to manage the BHA, which has all your extensive tools on there, you're also got to manage the problem you're solving in the first place with drilling with casing, raw circulation, depleted sands, wellbore stability. Another advantage of the retrievable system, if you're drilling harder formations, you can pull the bit out and change the bit out in case the bit goes early. Anybody have any questions?
How do you
Yeah,
retrieve it? So are you retrieving it on wireless?
Good question. You retrieve it on the drill pipe.
Okay.
Drill pipe. Okay. You had a question?
So you run a smaller gauge bit with the reamer then?
Yeah, exactly.
So
If you're drilling 9 5/8" casing in, you're going inside a existing 13 3/8, so you'll have an 8.5" bit on bottom and like a 12 1/4" under reamer, X feet above it. Yep, yep. Right now, the only two companies that have steerable systems that have been developed are Baker and Schlumberger. We're at Weatherford, we're developing a 9 5/8. It should be commercial here by the end of the year, but the problem is we're restrained by a lot of intellectual property constraints on design. But 95–96% of all drilling with casing build liner is non-retrievable. So, I mean, we're very much in the game there. All right, any more questions on that? Okay, let's talk about these casing bits. There's two designs we have right now for actual drilling with casing bit. The first is a Defier DPA design. D is for Defier, P is for PDC, A is for aluminum. I think one of you guys or girls asked about what the bits are made out of. Let's go to this next slide right here. This is one piece, the aluminum blades, aluminum nose. You've got nozzles here, but on top of these aluminum support blades, you've got thin steel rails. Okay, these thin steel rails house the PDC cutters. That's what's doing the drilling. So you ask, how is this drillable with a conventional PDC or rock bit? Well, there's 80 to 85% less steel in the drill out area replaced by aluminum, and that makes it drillable with PDC bit. A lot of people ask, what happens to the blades? What happens to the PDC? Sometimes we get steel shavings over the shakers, but we think what's happened is the PDCs, some of the steel, it's actually getting pushed out and ground up and pushed out in the formation, never to be seen again. We've got over 200, close to 300 runs right now with very, very few problems, if any. In other words, we haven't seen any cases to date of debris tracking us down hole in subsequent hole section.
Other questions?
These nozzles
Oh, okay.
are also drillable. They can either be copper or ceramic. We prefer the ceramic nozzles because they're good to 300 foot per second jet velocity, which is more than sufficient to get you the hydraulics you need. The copper nozzles we typically use if we're reaming with casing, but typically we don't pump as hard. Those are only good for about 90 feet per second. These thin steel blades are mechanically locked to these aluminum blade supports right here. So if you look at this thing, most of it's aluminum. Aluminum drillable with bits, PDC or rock bits. And it has 80 to 85% less steel than a comparable drilling with casing bit, like for example Baker's Easy Case bit, which is 100% alloy steel, requiring a separate PDC or a dedicated PDC bit to drill it out. And that PDC bit may or may not be the ideal bit to drill the next hole section. Yes, sir.
Does the bit wear as much as a conventional bit? Does it wear out?
This right here? We don't know because we don't pull them out. That's a damn good question. I don't want to know. The answer is it probably wears a little more. We have pulled it out when it's hit junk and stuff, so it gets torn up pretty good. But like I said, we've had 95% success rate where we haven't pulled this thing out. So all the runs, we don't know because it stays in the hole. I would think intuitively it would probably wear a little more just because you got more aluminum in there. Another thing to think about, one of the engineers, we designed these things in Scotland, one of the engineers up in Scotland was saying, why don't we make this thing more steel, more durable, so we can drill harder formations and just spin it on bottom a lot harder to wear away all the aluminum to make it easier to drill out. Well, that didn't make sense to me because you're kind of defeating the purpose. As soon as you get to TD, you want to go ahead and cement the thing in the hole. So this is the design right now, and it's here to stay. We can make these bits drillable up to 20, maybe 25,000 PSI unconfined compressor strength. People will ask me, what's the hardest rock you can drill or have drilled? We've actually drilled 20,000 PSI unconfined compressor strength rock only for 15, maybe 20 feet at most. What happens when we hit a hard streak, we'll back off the weight on bit to save the cutting structure so it drills its remaining section. Basically, you use common sense, good drilling practices in casing drilling just like you would in conventional drilling. Any more questions?
So, when you're drilling through this, are you drilling through with more casing, or you drill through with drill pipe? And
What, through this bit?
yeah.
We have drilled with casing bit through a casing bit probably less than 15 times. Yes, you can do that.
Okay.
Yeah. Think of drilling it, the procedures for drilling out these casing bits are very similar to drilling out shoe tracks with existing flow collars in there. If you're drilling it out with a PDC bit, you want to apply as little weight on bit on as possible to start. In other words, you don't want to spud in or jam the bit down on there, and gradually increase your RPMs to about 50, 60, and pump as fast as necessary to get all the cuttings up through there. Once you get through the bit without rotation, you want to pick up to make sure everything's free, then you go back down. If you're free, drill the subsequent hole section. Basically, really, it's almost identical to drilling out shoe tracks. You got to be careful drilling out shoe tracks. You don't want to get in a hurry, because what happens when you get in a hurry, you don't have effective hole cleaning, you can pack off, and you hate to get the casing stuck in the shoe track before you even start making holes. That all makes sense? Yep, go ahead.
How do you account for torque and drag? Because Rutherford is a CDS system I was reading before coming here.
Oh, yeah, we'll get to that. Go ahead.
So, I mean, when you're actually laterally in the hole, your casing is rubbing against the borehole,
Yep,
right?
yep.
So it's putting further stress, and
Yep.
it's hard for rotation.
Exactly,
So,
exactly. What we do calculations, side force calculations in our torque and drag modeling, and that'll tell you if you have issues. The way you can mitigate that is put some centralizers on there to minimize the wall contact. And we'll go into that. We've got centralizers that are non-rotating. In other words, that they stay fixed in relation to the wellbore, but the casing is rotating inside. So that's a way to mitigate some of those side forces. But yeah, when you get high dog legs, and we typically don't drill with casing higher than 3 or 4 degrees per 100 feet, as I'll talk about later. One of the things, and Lee brought this to my attention earlier, if we don't get that far tonight, this will be, you gonna post this on the internet? Okay, this presentation, and y'all feel free to call me after class or next week or whenever if you have any questions. The critical thing in drilling with casing is connection design, because that's what's going to come apart on you if you get into these high dog leg situations, or if you're rotating for a long time over a dog leg. If you get a phenomenon known as cyclic stress fatigue, and all that is wear and tear and fatigue stress, because you're rotating X revolutions across a bend in there, and it's naturally going to fatigue the pipe. So the more tortuosity you have in that well, the more prone you are to get some type of cyclic fatigue damage. I've got that later on in the presentation. Talk about this, the second type of bit we have is a softer formation bit. It's called a Defier DT 306, 406, 506. This is the amount of blades, 3, 4, or 5. It's only good for drilling up to about 7,000 PSI compressor strength. Very soft formation, typically surface casings. but we use it mostly for a reaming tool. And it's unlike other reaming tools because it actually has a bladed cutting structure right here. And why you need the blades, if you have fill in the hole, this will drill up existing fill. You've got interchangeable nozzles. Most other vendors' drilling tools only have ports. Ports don't give you the hydraulics as you would get in when you get to size your own nozzles. In other words, I could put 20, 30 seconds in here, 12 to 30 second nozzles, 26, 30 seconds, just whatever the hydraulics dictate for those specific hole conditions. All are PDC drillable, drilled out with a PDC bit or a rock bit, no dedicated trip required to drill these things out. Let's see, we're talking about that. Okay, don't get all hung up on this, I'll walk you through this. This is the fire DPA drill out PDC performance. Basically, this top number right here is the OD of the cutting structure. So let's take 12 right here. This is a 9 5/8 by 12 inch casing bit, a DPA 6413, 6 blades, 4 blades come to center, 13 millimeter PDC cutting structure. This is the distance that casing drilled, the 9 5/8 inch casing, and that's 1,000 meters, so that's about 3,300 feet. Now, this distance right here is the distance to subsequent drill out bit drilled. So in this case, it drilled about 1,417 meters, if my eyes are correct right here, which is probably about close to 4,000 feet. And this green right here is the amount of time it took to drill out this bit. So you can see all of them are less than 30 minutes, average about 10 or 15 minutes. That's how long it takes to drill out these casing bits, which are good to drill up to 20,000 PSI compressed with. That's really cool stuff. You don't have to make a dedicated trip.
I have a question. Where
Yeah.
I don't see a green bar, are you just missing the data, or was it just really quick?
Missing the data.
Okay.
I wish it was real quick.
It would be interesting to see the drill out time versus some of these lower where you didn't get as much well bore out of the drill out bit. See if that drill out time, if something went wrong in that drill out, that might have wore out that bit.
Yeah. I think a lot of times operators don't want our people on location because it costs them money. You know that from BP, man.
Well, and that, yeah.
Yeah. So a lot of times we can't access the data. Now, drilling out, the more blades you have, the harder formation these casing bits drilled is proportionally it's going to take you a little bit longer to drill it out. So you can see most of these bits right here were 6 bladed. We do make 8 bladed bits. Those are going to take a little bit longer because if the 8 blades come to center, you'll probably talk about 30 to 45 minutes to drill out, which is no big deal if you compare it to a separate dedicated trip to drill it out. Anybody else have anything on here? Okay, I want to show this slide right here. Contributions to non-productive time when you're running the casing and liner in existing open hole. In other words, running it or reaming it to bottom. As you can see, 49 or 50% of all the non-productive time is due to hole conditions. Not necessarily casing tools or seal assemblies on liners or thread design. So what this is telling you, this was a North Sea operator, I believe it was Statoil. The non-productive days in this case due to tight hole or stuck pipe was 57 days over a 2-year period. And this excluded the cost impact of setting the casing high. What happens when you don't set the casing at planned depth? You might have to run a contingency liner. Talking $1 million right there, especially in offshore operations. So the lesson learned to be here, if while you're drilling the hole and you're getting to TD and you're having problems pulling out of the hole or a lot of tightness on connections, things like that, think about putting a casing bit or a reaming shoe on the bottom of it to facilitate getting that casing to bottom. Don't put a float shoe on there. Do something that's gonna do you some good. Also have the ability to rotate that casing bottom. Because like I said, what's the definition of insanity? Doing the same thing over and over again, expecting a different result. Yeah,
So I guess you've kind of half answered my question already, but if tight hole and stuck pipe is the issue while running casing line, were these guys running a CRT where they're trying to pump and rotate the bottom?
don't know that. No, this slide's probably 10 years old. I don't know if they were. Yeah. I think this is probably offshore. I think these were liners right
Yeah,
here.
so just straight
So it was just the top drive.
Yeah.
Great point. That's why it's very important in the planning stages in the well. You guys are gonna be drilling engineers for an operator for a service company someday. Get the service provider in the well planning stage, because most of the money can be saved and it's proportional to the success of the project. If you can have all these tools lined up at the onset, rather than calling these companies the night before the job, say, hey, Steve, looks like we need a bid. Okay, when do you need it? Tonight? Oh, I can't get it to you for another 2 weeks. Plan this stuff up front and make it seem it's common sense, but people still don't do it. Partner with a service provider, whether it's Weatherford, we'd like it to be Weatherford, or Schlumberger, or Halliburton, or Baker. Get them involved, make them part of your team, so they can align with your drilling engineers, with your drilling staff, and make the right decisions up front, rather than having to wait till the problem's already there, and you start throwing good money after that to try to solve it. Does that make sense? This is just a detailed construction of the fire DT. Like I said, this is mostly used for reaming. Again, you've got aluminum right here. These blades are aluminum. You don't have PDC cutters, but pressed into the aluminum blades, you got 6mm chips of thermally stable polycrystalline diamonds. As this thing drills or reams, you wear away a layer of this aluminum, exposing another layer of TSP, or thermally stable polycrystalline diamonds. They're not as good for hard formations like PDCs, because PDCs are actually brazed into steel. They have a lot more structural integrity than these. That's why these bits are primarily used for reaming, unless there's a formation less than 7,000 PSI compressor strength. You can run copper or ceramic nozzles, just depending on the application. If you plan on exceeding 90 foot per second jet velocity, you gotta have ceramic nozzles. Questions? Yep.
Is
Why is this one only rated to 7,000 pounds? Instead
Great.
of 20 if this has
Yep.
like tons
Just
of
because of
power?
the cutting structure, you don't have PDC cutters right here in the cutting structure. These are TSPs, or thermally stable polycrystalline diamonds, and they're just mechanically pressed in. They're not brazed in, as you see with PDC cutters on steel blades, into steel blades. Yep.
Got it.
Yep.
what's the mechanism? I mean, drilling out the copper nozzle should be no big deal, but
Mhm.
drilling out the ceramic cutters, is it just chipping them off slowly, or you ever have any problems with the ceramic
Never had
ceramic
problems.
jets?
Yep.
Okay.
Drill them out, because we typically drill these things out with PDC bits, more of
Yep.
a shearing motion than a
Yeah.
milling type motion there, yeah.
So you
But
can
no, never seen an issue.
Okay,
with
good
the
deal.
ceramics. In conventional bits, they use tungsten carbide nozzles, which are
Yeah.
not drillable with PDC bits, yep. But no, answer your question, no issues with that.
Yeah.
Yep. Basically, let's look at this nozzles, the ceramic nozzles. This is a ceramic tube. This is a copper insert which holds that ceramic tube in place. These ceramic inserts, right here, they're actually threaded in, and the tube is threaded in with the insert, so they're pretty much locked in. So you're only really drilling out, I want to say about an inch and a half of ceramic tube. So, but no, there have not seen any problems there. Okay, this is a type of reaming shoe we use for highly tortuous wells when you want to run casing through high dog legs, typically greater than 5 degrees per 100 feet. We've used them in the Bakken Shale, we've used them in the Niobrara, we've used them in some other shale plays, the Eagle Ford shale play in South Texas. Reason it's designed like this is it's not gonna have a propensity to sidetrack the well. The last thing you wanna do is go in the hole with what they call an aggressive bit, or in other words, a bladed bit with a minimal amount of blades, where you could potentially sidetrack the well. This isn't gonna sidetrack the well because you really don't have any cutting structure, and the blades are kind of concentric towards center, curved towards the center right here. But it is a really good reaming tool. This also contains TSPs, or thermally stable polycrystalline diamonds, pressed into aluminum blades. You have PDC cutters, but they're on the external gauge. And the reason you have PDC cutters on the external gauge is that's where most of your reaming in the existing holes will take place. That's where most of your work is done. PDC cutters here, they don't get drilled out with the next bit because they're outside the gauge of the, outside the drill out area here. Any questions on that? Here's a reaming tool comparison I put together. These three tools, here's our Defier DT, here's the clean ream. This is a reamer shoe right here. This is a Schlumberger Warthog tool, a Baker Easy Ream, and a Davis Lynch penetrator. These right here are basically poor boy reaming tools. This you would only want to use if you have to get over a ledge or you have a light amount of reaming. Why do you think that is? This is just tungsten carbide. You've got ports and not nozzles. It's good to get over a ledge. It's also less expensive than these two tools right here. So if your only problem is getting over a ledge or some light reaming, yeah, you can run this tool right here. The Schlumberger Warthog, I still don't quite understand the design, but again, it's a scallop type profile. It's got open ports right here. If you have a minimum amount of fill and not bad to hold, you could probably run this. I don't understand the design right here. I've talked to some of the Baker engineers. It's got a concave structure over here, and they tell me the reason they designed it like this, their number one priority, was for ease of drill out. So I told the guy who was a friend of mine, I said, why would you not want to design it for the purpose it was intended to be used for? That is, getting your casing the bottom in tight hole with that hole condition. He said that's the way they wanted to do it. It has a center port right here, but again, no nozzles for hydraulics, and you have PDC cutters on the external gauge. So you would probably only run these if you had some tight hole, but if you had any fill on bottom, no way, Jose, you wouldn't be able to get the casing through there, or at least it would take you a long time to get it through there. The penetrator is just basically a dressed up float shoe. It's got some carbide buttons pressed on here. Again, you could probably use that if you're looking to save some money and you're just trying to get over a ledge. But if you've got some tough reaming, when you pull out a hole, you're reading those geolographs, you're seeing you're taking 30, 40, 100,000 pounds of overpull, that formation's coming in on you. One of these two cutting structures is the way to go. Like I said, you've got PDC cutters on the external gauge, you've got a cutting structure here to get through fill, and you can rotate, and it'll do you some good while you're rotating to open up that tight hole. Any questions on that? So I guess the moral of the story here, put the right reaming shoe per your application. Now let's go one step farther. If you see in your planning process that offset wells have shown a propensity to get, it's problematic getting casing to bottom, then think ahead. Make sure you've got the right connection on that casing. A lot of times we'll be asked by operators, hey, we've got an 8-round thread, which just means eight threads per inch. It doesn't have any torsional capacity. It has 0 cycle fatigue stress resistance. So what we have to do is put a torque ring on there. That's only good for torque, for a certain amount of torque. But what happens if you have to rotate for a long period of time? Like I said, it doesn't have the cyclic stress resistance, especially if you go in a directional hole. That pipe's going to come apart after X number of revolutions. So think ahead. If you see you're going to have problems getting casing in the bottom, have a buttress minimum thread, but a modified buttress would be better. Now, I respect that a lot of operators have already had the pipe bought up front, and they have to run that pipe. But so maybe we can get by with just a torque ring. But I've turned down jobs where we had to have some type of reaming shoe like this on the bottom what I call like an aggressive cutting structure, minimal blades that require some torque when you rotate. And their top drive was only good to about 15 or 20,000, and our torque and drag modeling showed we needed 30,000 to turn the pipe at 15,000. So they were pretty much screwed from the onset. So design the rig, design your casing for the problems that are anticipated. Does that all make sense to you? You do it up front in your planning process. You get the service companies involved up front. My boss would have been proud of me saying that. You got this recorded, Lee?
Yep.
Okay, here's the case history of a job where we used a clean ream tool to, this was in West Texas for Encana. Basically, they had an 8 3/4 inch hole, a lateral well 90 degrees, 5.5 23-pound, 95 grade VAM top. VAM top is a really good connection. It's got good torsional and cyclic fatigue resistance. They couldn't get the pipe down conventionally, so we put one of these 5-inch by 6 1/4 inch clean reams on the bottom. We had a ream about 1,000 feet, got the pipe down, and we actually had a top drive casing running tool, or what they call a CR tool, to be able to rotate the 5.5 inch to the bottom, and it all worked out good. They couldn't have got the pipe down with conventional methods. Another case, and this was actually for BP in the Haynesville Shale. This was back in like 2010. 8 3/4 inch hole, 90 degrees, lateral well, had a VAM SLI J2 connection, perfect for reaming with casing. Had a ream actually 4,100 feet. There was no way they would have got this casing down through the tight hole over that distance with just a float chute. We actually had a 14-degree dog leg in the unstable shale. So not only were you fighting the unstable shale, you were fighting that dog leg in there. So good thing we had this cyclic fatigue resistant connection. We probably wouldn't have got down. It took us, about over 50 hours to rotate this casing to bottom. But then again, we would never have got to bottom without the equipment. Yeah.
So $30 oil, running tapered strings,
Yeah.
does this affect anything?
Yeah, it affects a lot of operators' decisions. It sure does. One of our, that's a good point. Our cementation guys, the guys that design the float collars and the product line manager and the conventional reaming shoes, they're having to dumb down the reaming equipment, reaming shoes, because a lot of operators are saying, screw what I just said, we just want something on bottom and we don't want to pay the money for it. They want to take the engineering out of it and they want to put the cheapest tool on the bottom. So it goes exactly what you said. People aren't making good decisions. And this was Colombia, I don't know in the US, but that's really stupid if you ask me. So here, it's a definition of insanity, and you're not going to get the pipe down. Maybe you're putting a shoe that may or may not be the right application. So yeah, operators are looking for really cheap methods. But that's ridiculous. They're trying to dumb down their product line by making these really inefficient reaming shoes just to satisfy some Colombian operators' requirements, you know. We're competing against the Davis Lynch's, the Top Goes, especially reaming product companies. And a lot of times, they're not specific to the application. So in other words, if they have a lot of fill on bottom, they're still running shoes without blades, so you're going to spend hours upon hours trying to ream through that fill, and you don't have a cutting structure. You follow me? So yeah, it sure as hell does have an impact on some of the decision making, whether it be good or bad. Any more questions? Questions? Yep.
Is this casing reusable? I mean, the one with the BHA and stuff? How do you know how much it wears and tears?
Oh, you talking about the casing?
Yeah.
The retrievable?
Yeah.
No, the retrievable casing stays in the hole. It's just the BHA that comes out of the hole. Yeah. But to answer your question, if they pulled it out, it would probably be reusable. Which brings another point. Most of our casing drilling applications is done through pretty benign formation, non-abrasive formations. Like I said, less than 20,000 PSI compressive rate. So you're not sustaining damage to the casing. In the event you drill through abrasive formations, 25,000 PSI, you probably want to put some type of wear sleeves or some type of hard banding on the connections. But that's typically not a good casing drilling application, because you're trying to solve a problem, but you're also tearing up your pipe, and your ROP's rate of penetrations are gonna be so slow, that's probably not gonna be economical to drill that casing in. So to answer your question, the casing's probably still good if indeed we had to pull it out of the hole, yeah, based on the formations we drilled. Any more questions? All right, let's see. Casing drive systems. Okay, you gotta have a way to turn this casing, and there's several methods. A lot of your HST rigs right now have what's called CRTs, or casing drive systems, built into the cost. So you already have the capability to rotate your casing to bottom if you need be. So, which leads me to my next question. Why not be prepared and have a decent connection on your pipe if you know that rig's got that ability to rotate your pipe to bottom, you know? Why put an 8-round thread on the bottom if you're anticipating some problems in that respective hole section that you can run that casing in? Makes sense, huh? Okay. Okay, the overdrive casing running and drilling system is good to up to 750 tons, just depending on the size of the rig. The beauty, there's no modification to existing top drive structure. It's remotely operating. You're only 1 or 2 people on the rig floor at all times, nobody up in the derrick. Removes the need for conventional casing running equipment. Multiple safety interlocks. Well, all that means is there's really no way to drop that casing in the hole. So when your elevators are shut, when your casing spider is shut, your elevator is released, and vice versa. When your what do you call it, casing tongs are released, your spider is shut. So there's really no way, it's got a built-in interlock, there's no way for you to drop that casing in the hole. You can also push down, reciprocate and circulate, and rotate the casing if required. Difference here is pushing down. It's very hard in some of these long laterals to get you enough weight, even using the top drive, to push the casing down, because you really don't have good gripping elements with the rig's elevators. What these have right here, the overdrive system, you can put up to 10 or sometimes 20 metric tons of top drive weight, usable weight, to help you push the casing down when you can't run it down conventionally. Lee, you were telling me you had some problems with that in Baca when you were working there, getting pipe down.
But yeah, any long laterals, you gotta sometimes you gotta go outside the box to get it down.
So this system has the ability to put usable top drive weight down on the casings. Also, there's a method operators will use called floating the casing in. Y'all familiar with that term? In other words, you use air in X amount of casing and make it more more mobile in the hole to allow you to push that casing to the bottom. So it more or less floats in there rather than sits, if you can visualize that. So they'll calculate how much void space in there before they start putting mud in there to facilitate getting casing to the bottom. Also, another feature, it's got a torque sub on it, and basically it measures the true torque of the casing in the slips. It takes out the erroneous readings you can sometimes get from the top drive torque, and it gives you a more accurate torque, so you know exactly what that torque sitting in the slip, what that casing is being made up that's sitting in the slips, rather than just looking at the top drive torque measurement. Because there could be some frictional forces in there that are not accounted for with the top drive torque.
Does this just make up to your saver sub?
Yep.
Okay.
Yep. So, yep.
They mostly use this in the Bakken just to run the liner, but not actually to drill.
Actually, you use this mostly to run casing and not the liner, but remember the liner, by the time you get to the liner, it's still gonna be in case hole. The only time you would use something as expensive as this to run the liner is if you're running the liner and some of the liner gets into the open hole, you follow me, and you may need some reaming. But since a lot of times your liner is still in casing, by the time you switch over to drill pipe, you would just use the top drive to rotate it down.
I've seen this or something similar on Precision 825 in
Mhm.
Bakken, and it was a single rig, single joint, so I guess maybe that's why they were using this to run linemen. They're running
Yeah.
a liner hanger.
This would be, now, if you had a really long, say you had 10,000 foot of open hole, and you were hanging the liner like 1,000 feet from surface, yeah, 90% of your liner would be an open hole, so you would want something like this on your liner while you're running it, just in case you got in a bind, and then you would have to switch out to drill pipe once you got all your liner run. You have to change out your handle fluid casing to the drill pipe. What was it? Does that answer your question pretty much? Any more questions on this?
This whole thing froze.
Okay, if you guys need to go to the bathroom or whatever, now's the time.
Take a break.
You got 5 minutes.
We got a freezing problem.
Dude, I think they put like chocolate.
To go up that thing. Maybe caught it and then doing them came off of it.
Culinary adventure.
Yeah, there's a whole bunch of them that ran away. Yeah, dude. I'm not scared of them, but then that would scare the shit out of me.
Can you pause for 1 minute?